Hello, so we have learned how to create equilibrium expressions, KEQ, of the equilibrium constant. We learned some of the rules to manipulate them and some of the rules that when there are exceptions to it. And so today what we're going to learn is how do we use once we have a KEQ or once we have some data in there, how can we use that to kind of calculate the KEQ value and what are the kinds of setups that we're going to have to use for these KEQ expressions. Um, there's a fair amount of math involved in this. We're going to learn a new kind of technique for how this works, and we're going to yeah, a new technique to kind of set up the data that we get, and we're going to calculate some KEQs. So these are just straight examples. There's no new kind of theoretical idea of chemistry in here or anything. It's all just straight math and data and all that fun stuff. So here we go. All right, so in this case, we're given a, a formula. H2 plus I2 goes to 2HI. We're given some initial concentrations, so the initial concentration of H2, the initial concentration of I2, and then we're given an equilibrium concentration. And we're asked to find what is KEQ. So we're looking for a numerical value in this case, right? But if ever we're looking for a numerical value, a good place to start is with the KEQ expression. And so we remember that that is products. And we have an exponent of 2, of course, because it is the over reactants times the concentration of I2. Right, so we've got products over reactants. We have the concentration of the products and it's squared because of the stoichiometric factor. And then we have the concentration of the reactants. Right, now the problem is that we only have one of these values because KEQ, remember, is only a number that this number only applies to the equilibrium concentrations. So the only one of these that we actually have is this value. So we can plug this value in here and figure out KEQ from there, but we can't kind of we can't complete it. We don't know what the KEQ is because we don't know the equilibrium concentrations of H2 and I2. And so to figure that out, we are going to create a table. I'm going to rewrite the KEQ over here because I switched slides and so now it's gone, right? And in this table, you're going to notice that there's 3 rows, right? The rows are the initial concentrations, the change in concentration, and then the equilibrium concentration. These values, right? These values in this row are going to be the ones that are going to go into our equilibrium expression, right? So we need to fill in this bottom row in order to get to what we're going to be able to plug in to find out KEQ. What we're given is we're given an initial concentration of H2, we're given an initial concentration of I2, and we're given an equilibrium concentration of HI. Right, now we can assume that the initial concentration of HI is 0. So let's assume that we're not adding all 3 components and then seeing what happens, right? Usually we add the reactants and see what comes from products. So given that we have the initial concentrations of all 3, right now if we know how much those change as this reaction reaches equilibrium, we'll be able to figure out the equilibrium concentrations because we'll just take the initial amount, add in the change, and we should get the equilibrium. Now there's only one that we can figure out so far, right? If we go from 0 to 1.87 times 10 to the negative third, it stands to reason that the change in concentration is 0 plus 1.87 times 10 to the negative third, and that gets us here. Okay. But now what, right? Now it seems like maybe we need to take a step back and figure this out because we don't have values for any of these 4 blanks over here in this quadrant. This is where we go to the balanced equation. So we use the balanced equation to figure out the relative change for all components, for all reactants and products. right? Because what this balanced equation is telling us is that if we react 1 mole of H2 with 1 mole of I2, we get 2 moles of HI, right? So if we react some number of H2 and some number of I2, we get 1.87 times 10 to the negative third. We know that the change in concentration of HI, right, delta HI is equal to 1/2, or sorry, is equal to 2 times the change in H2, right? Because if for every mole of H2 that we produce 2 moles of HI, right? So we could also write this, if I move this 2 to the other side, right? We could also write this 1/2 the change in concentration of HI equals a constant change in H2. So we can do that. We have a number for the change in concentration of HI. It's 1.87 times 10 to the negative third. And we can do half of that over here, and this is 0.935 times 10 to the negative third molar. Now we're going to make this one negative because the reactants are disappearing while the product appears, right? So the products are appearing, the reactants are disappearing. The change is positive for the products and negative for the reactants. And then what value goes here? Should be the same value, right? Because they have the same stoichiometric coefficient. So now we've got values to fill in at each one of these, right? So these numbers, if I wasn't clear, right, if we just plug in 1.87 times 10 to the negative third, right, that's how we get the change in the concentration of H2 or I2. We take 1/2 times 1.87 times 10 to the negative third, and we get 0.935 times 10 to the negative third. Right? This isn't good scientific notation, but because we're going to be adding these two, the initial and the change together, because we're adding those two together, I'm not going to mess with the factor of 10 that we're using over here, because we want to be able to do this subtraction easily, and we can, right? 1 minus 0.935 is 0.065 times 10 to the negative third molar, right? So just adding these two things together, the initial plus the change. Do the same thing here, initial plus the change, we get 1.065 times 10 to the negative third molar. And now we have filled in all 3 positions of the equilibrium row of our table. So we have equilibrium concentrations for HI, we have equilibrium concentration for H2, and we have equilibrium concentration for I2. So we can plug these numbers in over here. 1.87 times 10 to the negative third squared divided by 0.065 times 10 to the negative third times 1.065 times 10 to the negative third. And we multiply all this out and we get a KEQ that equals 51. So I'm not going to go through the math of all that. That's just plugging it into the calculator and calculating all of that out. But notice that even if we're not given equilibrium concentrations of all of our components, we can actually figure that out. If we know our initial concentrations and we know one thing about where our reaction ends up, right? We only need to know one of these equilibrium concentrations to figure out the rest, especially if we know our initial concentrations. Okay, so that's one example. I'm going to do another one. I'm going to set it in a separate video just so it's not too long. The next example is very similar, but we start with a slightly different set of data. So I hope that works, and we'll see you in the next one.